Thank you very much. Good morning, everybody. Can everybody hear me? Good. Okay. So I'd like to thank all the organizers for the chance to be here today to share our work on the ICONS program. And I'd like to start with a question. So given some uncertainty in things like access to clean energy or access to clean water or even the state of the climate, how many people here are concerned about the future? Me too. And this is the problem that brings me here. Now, I know that we're all here because we think that there's some problem, and I'm going to try to add this problem to your plate of problems. This is the thing that keeps me up at night, is the fact that I don't think we're training our students to succeed in these big problem areas. So I hope that when I'm done today, you'll not only think about ICONS as an important, interesting, program to try, but maybe even a program that's crucial for our future. So ICONS, which stands for Integrated Concentration in Science, is an effort to bring these big problem areas of strength at the graduate level at UMass and at many institutions into the undergraduate level with a very different way to teach science. Now, students, when they come, they show up on campus and they're faced with a choice of many different majors in engineering and science, and these attempts to teach the knowledge and skills that you need to solve the problems that fit into each silo. But what about the problems that don't fit? For example, like making a new drug where you need to know about the biology of disease and the chemistry of new drugs and the physics of how drugs bind onto targets and the math and stats of trials. Who's an expert in all that stuff? And there's lots of examples, like making biofuels, where you need to know the biology of plant matter and the chemistry of new drugs. And I think you get the point. The point is who's an expert in all of this stuff? And this is really the driver for why I'm here today, is how do we train students to succeed in these big, multifaceted problems? And I would actually say that all the problems that students face when they get into the real world have this kind of characteristic. And so that's the driver. Now, a standard approach is the interdisciplinary science major, where students take a couple courses in columns A and B and C and D. And right off the bat, you know the problem. They're not an expert in any field. Good luck getting a job. And they still haven't had the experience to try to integrate ideas to solve problems. So in 2009, a very diverse team of faculty and staff came together at UMass. And I should add that the chemical sciences are very well represented here. And you could say, why is that? Well, we brand ourselves as the central science. And that's got to be good for something. What's the use of that? The use is that we can be the hub of integrated science. So this very diverse team came together to address this grand challenge. The grand challenge is, how do we train our students to be not too narrow and not too broad? And it dawned on us, that if a very diverse team is good for faculty and staff to solve grand challenge problems, it should be for students as well. And so that's the basic idea of ICONS, is if you imagine having diverse teams of students working on today's big problems. It's training for the real world. So, for example, you might have a biology major and a chemistry major and a student majoring in physics and a student majoring in math working on a big problem that's making news in, for example, the field of biomedicine. And like the light beams of the Death Star coming together to make a super powerful beam, we're not trying to blow up a planet, we're trying to save the planet here. They could shed new light, and it doesn't have to be, it could be a problem on energy, it could be a problem on climate, a problem on water. Whatever the problem is, it has to take this group of students and forge a team out of them because they have a shared mission. They're working on a problem that they care very, very deeply about. So that's the backdrop. I was asked in 20 minutes talk about the drivers, the innovations, and the barriers. And of course, I don't have time to talk about all that stuff, so I will focus on these items. But I hope at this point I've impressed upon you that there's yet another problem that we need to think about, and that's how to train our students to address these big problems. The reason why we know that that driver is there is because we haven't solved them yet. And that brings me to the mission of ICONS, which is we want to make the next generation of leaders in science. They're going to be armed with certain attitudes, knowledge, and skills that they're going to need to address these big problems. And I want to take a step back and think about the word leaders. Of course, we know not every single ICON student will become a thought leader or a business leader or a political leader. Many of them will. But when I think about leadership, I'm really thinking about something that you mentioned yesterday, is we need students to take ownership of their work in college and outside of college. Okay, so now the question is, how do we actually reach this mission? Now, I'd like to say that we scoured all the literature on how people learn, but we did not do that. Instead, what we did was we had a room filled with faculty, everybody writing student outcomes that they wanted to have on sticky notes, and the walls and the ceiling were covered with the sticky notes, and we tried to organize them, and when the smoke cleared, we came up with the ICONS learning goals. And I really harped in some of my comments yesterday about the importance of articulating the learning goals, and I don't think it's just the students need to master, the material. They need to master quantum. They need to master thermo. They need to master kinetics. I think it's beyond that. So this gives you a sense, and I won't read through the list, but I will breathe some life into some of these. So item 1 is the fact that we present science problems to our students. And you know what? We've already skipped a step. Some of the time, not all the time, but some of the time, we need to present societal problems to our students so that they can chew into that and think about what's the role of science, giving them a chance to actually frame their own questions. Item 4 is about the fact that students, when they bump into these big problems, get very qualitative. This is either good or bad. They don't have the nuance. We need to train them to have the quantitative nuance to realize that certain solutions have a regime. Item 7 seems like it's obvious, carrying out scientific studies. But the things on the end here are key. Students need to design their own studies, and they need to be able to connect the dots to societal challenges. And then item 8 we talked about a lot yesterday, communication, the C word. Not only do they have to, so I'm going to add, we heard from Bob 2 words, but I'm going to add persuasively to compel action, not only to scientists, but to non-scientists. That's crucial. And items 9 and 10 are attempting to instill the habits of mind to make these students into lifelong learners. So after we came up with this, we're very gratified to see that these transferable skills, that's the name that I'd like to add to them, map very nicely onto this group of skills that came out of this study, the cognitive, the interpersonal, and the interpersonal. And I was also very happy to see somewhat after the fact that when you look, here's a table in the PCAST document that we heard about yesterday, there's really an excellent mapping onto these crucial elements of successful STEM programs. So now that we see that, the question is, well, what is ICONS? ICONS involves 18 credit concentrations. So right off the bat, you know this is not a major. It doesn't replace the major. Every student in the program is a major in some field of engineering or science. That major is the cake. ICONS is the icing on that cake. And that icing is in the form of case studies, lab work, and research. And every single project in the program has these 4 essential elements. Problem-based engineering and science. Instead of opening up a textbook, students start working by opening up the newspaper. That's the list of the problems of the day. As I said, they work in diverse teams. They also engage in student-directed learning. And I want to give you an example. The very first case study that we had in ICONS was cholera in Haiti, which a couple years ago was a very big problem making news. It actually is still a big problem. It's just not making news. And so we challenged teams to think about what are science studies that could address the societal problem. One team said, we need to sequence the genome of the cholera bug. We can use that as a signature of the spread. And that's a very interesting study. It's actually a field called molecular epidemiology. So freshman students came up with that idea. That's a great idea. But another team said, you know, that's interesting, but it doesn't solve the societal problem. People are dying now. They need to boil the water. They don't have, you know, they don't have the resources, the energy resources that they need to boil the water. So because Haiti's in the tropics, we need to study the properties of solar heating. And although that's not going to boil the water, it might be enough to partially clean up the water. So you see how different teams are looking at a problem through the lens of their passion and their interest. Now, we heard from Jim Anderson the question about top-down teaching versus bottom-up teaching. And when we have these, you know, two extremes and we're forced to pick, my answer is I'd like to do both. And I'd like to give you a feeling for how icons, how this works for icons. So in order to do that, I present to you this onion. And when students come into college, they're often really interested. Maybe they come into college, they want to major in science because they had a fantastic high school teacher, but also very often they've been hearing about these problems that they'd like to solve. And I consider these big problems that they've been hearing about the outside layer of the onion. So then they join a major and they start hacking into the basics of the major, forces in physics, atoms in chemistry, cells in biology. And this is crucial. This is how we think about the world. This is the language of science. And then as they go through college, freshman year, sophomore, junior, they reach and they start working on ever more complex problems. But to be honest, in the limited amount of time, they don't often get to the outside layer of the onion. In icons, they not only are working from the bottom up, but they're starting from the outside and they are drilling in the effort to see the entire onion. So I've talked about a lot of generalities. I'd like to give you now a concrete example of what an icons case study might look like. And I'm going to use a subject that I think is really very weak. And so you might imagine that you're teaching a lecture on sugars, on carbohydrates. You give a definition, you maybe give some examples, some structures, some of the chemistry. And for some students, they'll be really excited about this, but other students, they're wondering why they need to know this. And so in a best practice is shown here for what a scientific case study might look like, where you expose people to a problem. They think about, well, what do we know? What are the known knowns? What are the known unknowns? Then they go and they hack into the problem and they report what they found. We use slightly different language of inception, which is reading that students do prior to coming to class. They come to class and there's a big overarching question on the board that gets them to think about what do they know. They eventually research, create. Now the research thing, this is an interesting thing. It kind of raises the question now that we have, you know, the internet and Google and search engines, where there's a huge amount of information out there. How would that change the way we teach, you know, science? Because that's crucial for the kind of research that they do. And then students would reflect. So in the context of this, we could imagine a case study on high fructose corn syrup. And again, we'd start with the newspaper. So in the year 2010, we find that high fructose corn syrup comes much more weight gain. 2 years later, high fructose corn syrup is just fine. It's sort of like eggs are good, and then the next year eggs are bad, and then the year after that eggs are good. What's going on here? And so students really have to, you know, hack into the question, why are these outcomes so different, figuring out the known knowns, the known unknowns, and then the goal is for them to understand what are the limitations of these studies and how would they try to design a new one to address them. Then at the very end, a key step, the reflection step. Each student thinking, what did I learn? How did I learn? Why did I learn it? And what would I do next? In terms of not only getting more knowledge, but putting these ideas into practice. Now, let me ask you this. At what stage of college should we start a program like this? What do you think? Excellent idea. I couldn't agree more. So we think that ICONS needs to be a 4-year program because this effect needs to be built in. So we start actually with freshmen in a first course where it's really the introduction to working in teams, working on case studies. This is a big shift. It's a big shift in attitude because students are just used to working on problems where the answer's in the back of the book. Now they're working on problems where there's no book, no answer. So then after this, students choose a theme. Right now we have 2 themes available, biomed and energy. And in year 2, the cohort splits into 2 theme-specific courses focusing on communication, reading, writing, speaking, and debating on the issues that are relevant to the theme. In year 3, they get into lab, where they're actually having to design their own experiments where they connect the dots to problems. And at that point, and this point, all these students are actually in groups, in research groups, and in year 4, they apply all this attitudes, knowledge, and skills to hit the ground running with the research that they have. So I'd like to give you a feeling of the build-out that we have to date. Where are we? So we're in the 3rd year of the program. We have 3 cohorts coming from 20 different majors in engineering, in the College of Engineering, the College of Science, and the College of Public Health. We have built the first 5 courses. ICONS 1 and 2 were built from a grant from the Dreyfus Foundation. Thank you, Mark. And year 3 was built with a grant from the National Science Foundation. Thank you to Susan. And we actually have some adoption partners and a very diverse group, a high school, a community college, all the way to the Swiss Federal Institute of Technology, which the Dean of Science there had learned about ICONS, got so excited, came out for a visit for lunch to hear about ICONS. Now, at this stage, I'd actually like to show a short video, because I think it's important to hear the voices of the students. And I have to warn you that this is a somewhat of a kind of promotional video. So if you just extract that from your mind, because this is, this is about rigorous, science here. So just extract those kind of promotional portions from your mind, and let's see what the students have to say. Everybody here? Okay. So now the big question, of course, is does any of this work? Which leads to the question, what does Scott know about assessment? And my sort of tongue-in-cheek answer is 2 to the 3rd power, which is good because I'm using exponential notation. But 2 to the 3rd power in this context means that we're interested in formative and summative, qualitative and quantitative, generic and targeted instruments. And of these 8, we have implemented 6. And of these 6, I'd like to share with you a summative, quantitative, and generic instrument. And the reason, the fact that everything has a pro and a con, it's a con that is very generic because it's not measuring the particular goals. But the pro is we get to compare with a lot of other courses. So this is the so-called SERDI at UMass, the student response to instruction. And what we're doing here is we're comparing the 21 sections, honor sections of a broad swath of subjects, roughly with the same class size. And we want to ask the question, is there a signature, even in this very generic instrument, of the icons effect? So first, I look at areas where icons, which is the black bar, is doing well. And the ones that really kind of tickle me are 5 and 9. 5 is instructor-inspired interest in the subject. Of course, that's what we're supposed to do. We're giving students the juicy stuff right off the bat. So it has to be interesting. And item 9, instructor-stimulated student participation. Of course, that should be off the charts. So where does icons fall short? Items 2 and 3. Instructor explain the course material, clear points of confusion. There's no way we could do that in icons with all the different teams working on different content areas. That's not the job of the icons instructor. The job is to facilitate process, not to deliver content. So the fact that this is actually coming up short is a signature of the way that we teach. The one red flag is item 7 here, which is that I received useful feedback. And that's something that we have since improved. And so what you might consider as the summatives are that even though we don't explain the material, we do inspire interest. We get students to take ownership of their education, and students feel like they're learning a lot. Now, of course, there's a difference between students feeling like they're learning a lot and students learning a lot, and so that's why this is the first step. But I want to echo a statement that Angie made yesterday, which is this is extremely frustrating for the students. They're working on problems and they're not putting a box around the solution and knowing that they're done. So this is a very frustrating way to learn for students, but that frustration is productive. Okay, so now what I'd like to do is I'd just like to ask the question, is this a repeatable kind of a signature? And so I'm now comparing icons, the first running and the second running, and that's shown here. And so the black is 2011, the white is 2012, and you see a repeatable kind of a signature. And now the question is reproducibility from, say, Icons 1 course, which is for freshmen, Icons 2 for sophomores, which focuses on communication. And so that's shown here. This is also against the comparison group. And again, we see explaining the subject, not so much. Student participation now is off the charts. And so what we see here is that even though, as I said, a very kind of generic instrument, there's still a signature of the icons teaching approach. Now the question is, okay, but wait a minute. Here's, as a quantum chemist, I tend to think of the world in terms of a Hamiltonian matrix. And so here's an example of a Hamiltonian matrix where you have all the UMass faculty on the one axis and all the students on the other. So the icons program is just this little box here. And if the impact of icons were only in that box, that wouldn't be enough. And so the question is, what's the impact outside? And so one of the main impacts is that when we've got faculty flowing into icons, teaching for 2 or 3 years, and then flowing out, it does change the way people teach. And so some examples are we've instituted these student-driven team projects in all of these courses. And the key elements, I should have put team in this list. The key elements are context. Students need to understand why they are learning what they're learning. The second one is ownership. Students need to feel like they're owning it, like they are part of the process of building the syllabus and reflection. They need to, after they think that they've learned something, they need to reflect on, well, what did I actually learn, why did I learn it, and how did I learn it? So those are key. An example is when I teach PChem now. Students come into the class. It's the first day of PChem. I have taught them nothing. I tell them to form teams, come up with a question. And of course, their heads explode. What do you mean, come up with a question? I tell them, when you were 3 years old, your parents couldn't, shut you up. You were a question machine. You're a chemistry major now. You're telling me you can't come up with a chemistry question? I say, well, when you put it like that, I was just thinking the other day about the blah, 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 blah. So they go back into their teams. They form questions, and we use computational chemistry to answer those. They have no idea how it works, and it doesn't really matter. They need to see the power of the approach. Then at some point, somebody raises their hand, and there's like, by the way, how does that software work? Ah, that's the entree to the subject, but not before. Okay, so what I'd like to end with is what I believe is the big problem, and that is the big problems of our day, and that we're not training our students to solve these. And the take-home messages are that education is not filling a bucket, it's lighting a fire, and we light that fire through context. Tell me and I forget, teach me and I remember, involve me and I learn. The difference between remembering and learning and the role of student ownership. A genius is someone who's made every mistake once, and the value of reflection in converting a mistake into genius. And finally, that the greater danger is not that our aim is too high and we miss it, but that it is too low and we reach it. And so with that, I'd like to thank you all very much.